In November 1959, on a hillside outside San Diego, a group of physicists watched a small aluminum spacecraft rise into the air, propelled by 5 explosive charges detonating one after another behind a curved steel plate at its base. The vehicle rose several dozen meters, remained perfectly stable throughout the ascent, and descended by parachute onto the sand. It was the first successful flight of a pulsed-propulsion spacecraft prototype in history. The explosive charges that day were conventional. The physicists intended to build the full-scale version next. That version would use atomic bombs, small ones, 2,000 of them, detonating in sequence behind a steel plate 400 feet across. The vehicle would weigh 4,000 tons at launch. It would carry 250 people to the moons of Saturn. Departure was scheduled for the American bicentennial in 1976. Almost built. Case number 108, the spaceship pushed by nuclear detonations. Theodore Taylor was 32 years old in the summer of 1957 when he left the Los Alamos National Laboratory and moved his family from the Mesa in northern New Mexico to a modest house in the coastal hills above San Diego. He had spent his entire adult career designing nuclear weapons. He had joined Los Alamos in 1949, straight out of graduate school, and had been assigned to the theoretical division under Robert Oppenheimer's former protege. Within 5 years, he had become the youngest weapons designer in the American nuclear program to lead a project of his own. He had designed some of the smallest and largest pure fission devices in the American arsenal. He had designed a bomb that fit inside a 5-foot cylinder and produced a yield of 500 kilotons. He had designed a warhead so small it could be carried by a single soldier. His colleagues at Los Alamos considered him the most naturally gifted bomb designer of his generation. He was leaving the weapons program because he had a different idea for what to do with atomic bombs. He wanted to use them to send humans to the outer planets. He was joining a small research group at a private company called General Atomics, which had recently received a $200,000 contract from the newly formed Advanced Research Projects Agency to study a concept called nuclear pulse propulsion. The concept had originated in a Los Alamos memorandum written in 1946 by the Polish-American mathematician Stanislaw Ulam. The memorandum was 3 pages long. The idea was simple to describe. Attach a heavy steel plate to the bottom of a spacecraft. Detonate a small atomic bomb a short distance behind the plate. The plasma from the explosion would strike the plate and push the spacecraft forward. Repeat the detonation once every 1 to 3 seconds. Thousands of times. The math suggested this would work. Taylor believed the math. He had spent 10 years watching atomic bombs behave exactly the way the mathematics predicted they would behave. If Ulam's calculations said a bomb behind a steel plate would push the plate forward without vaporizing it, Taylor was prepared to trust that conclusion until a physical experiment demonstrated otherwise. The world in 1957 was preparing for a space race the American public had not yet fully understood. The Soviet Union had launched Sputnik in October of that year, followed within a month by Sputnik 2 with a live dog aboard, followed almost immediately by preparations for a manned launch. American school children were being taught to hide under their desks in the event of a Soviet nuclear attack delivered from orbit. Newspapers ran daily columns titled Space Race. The Eisenhower administration had responded by creating 2 new federal agencies within 4 months of Sputnik. One was civilian. It would eventually be renamed NASA. The other was military. It was called the Advanced Research Projects Agency, and it had been given a mandate to fund anything, however unusual, that might close the gap between American and Soviet space capability. Its founding director had authority to approve contracts without normal congressional oversight. Every major American aerospace company was preparing proposals, chemical rockets in every possible configuration, ion drives producing continuous low thrust, solar sails using photon pressure from the sun, nuclear thermal engines that would heat hydrogen through a solid reactor core and expel it as propellant. Each concept had inherent physical limitations. The largest chemical rocket then being designed, the Saturn V that would eventually launch the Apollo missions, would carry approximately 150 tons to low Earth orbit and require the overwhelming majority of its mass to be its own propellant. The rocket would burn for 11 minutes to reach orbit and then be discarded. Nuclear pulse propulsion had no such limitation. According to the calculations produced at General Atomics between 1957 and 1959, a nuclear pulse spacecraft could carry 10,000 tons to Earth orbit. It could deliver 1,000 tons to Mars in 3 months. It could carry a crew of 250 people to Saturn and back in 7 years. The upper size limits of the vehicle were not defined by physics. They were defined by how many small atomic bombs a nation was willing to manufacture. Any spacecraft that could carry 250 people to Saturn was worth almost any political price. Taylor thought so. Freeman Dyson thought so too. Here's what almost was. Freeman Dyson joined Project Orion in the summer of 1958. He was 34 years old, British by birth, American by adoption, and already considered one of the finest theoretical physicists alive. He had done foundational work on quantum electrodynamics with Richard Feynman and Julian Schwinger. He held a permanent chair at the Institute for Advanced Study in Princeton, the position previously held by Albert Einstein. He was leaving Princeton for what was intended to be a summer sabbatical to work on a nuclear spaceship because he believed it was the most important engineering project of the 20th century. His mentors and colleagues at Princeton were puzzled. His wife, who had a small child and was pregnant with another, moved the family to a rented house near La Jolla for what would become a full year in California. Dyson would later describe his year on Orion as the happiest of his professional life. He was working with the finest weapons designer in America on the peaceful use of atomic explosions. He believed humanity would establish permanent settlements on the moons of Jupiter and Saturn within his own lifetime. He believed his own children would live to see this happen. The engineering was more elaborate than the initial concept suggested. The spacecraft would carry between 1,000 and 2,000 small atomic bombs in an internal magazine that ran along the central axis of the vehicle. Each bomb would be ejected downward through a central shaft toward a point approximately 100 feet behind the base of the spacecraft. The bombs would detonate on a precise timing schedule, once every 1 to 3 seconds during the launch sequence, and less frequently during the extended coasting phase between planets. The steel pusher plate at the base of the spacecraft, 400 feet in diameter for the largest design, would absorb the plasma impact from each detonation. Enormous mechanical shock absorbers between the plate and the crew compartment would smooth the sequence of impacts into something the human body could tolerate. Passengers would experience a series of firm nudges rather than continuous acceleration. The internal environment would remain roughly 1 gravity throughout. The first working design called for a vehicle weighing 4,000 tons at launch, roughly the mass of a naval destroyer. It would carry a crew of 150 for the initial Mars mission planned for 1965. Later designs scaled up to 10,000 tons and 250 crew for the Saturn mission planned for 1970. The passenger version Dyson personally preferred was even larger and included a complete self-sustaining biosphere, hydroponic farming decks, machine shops, laboratories, a hospital wing, and equipment for a permanent settlement on Saturn's largest moon. The vehicle would take off from the ground, directly from the ground, using atomic bombs. The engineers calculated the fallout consequences carefully. A single ground launch using the specified low-yield pulse units would produce approximately 1 to 10 additional cancer deaths worldwide over the following century, distributed statistically across the entire human population. Taylor and Dyson believed this was an acceptable price for opening the outer solar system to human civilization. Most physicists who reviewed the calculations agreed with the mathematics of the estimate and disagreed with the ethical conclusion. To demonstrate that the propulsion concept would work at all, the General Atomics team built 2 conventional explosive prototypes at the Point Loma test site south of San Diego. The first was called Put-Put. It stood 4 feet tall and weighed 300 pounds. It was made of polished aluminum with a small curved steel plate at its base. On the morning of November 10, 1959, the small team gathered at the test site with a 16mm film camera and a stopwatch. The weather was overcast. The engineers had rehearsed the sequence dozens of times on paper. None of them had ever watched a pulsed propulsion vehicle actually leave the ground. Put-Put flew several dozen meters vertically using 5 conventional charges detonating in sequence, remained stable throughout the flight, and descended by parachute onto the sand. It was the first successful demonstration of pulsed propulsion in history. Every person present understood what they had watched. The math had worked. The vehicle had stayed upright. The shock absorbers had absorbed. Everything the theory had predicted, the hardware had performed exactly. The film footage of that flight still exists. It has been declassified. The second prototype, called Hot Rod, was larger and flew successfully several times in 1960 and 1961. Some flights reached over 100 meters in altitude. All of them confirmed that the pusher plate concept behaved exactly as the calculations had predicted. The engineering worked. The only remaining question was whether the atomic bombs would work as designed when scaled up to full flight configuration. Taylor was certain they would. He had designed them. The Air Force took over primary funding of Project Orion in 1959, after the initial DARPA contract ended. The Air Force had a specific interest. It intended to use the completed vehicle not as a scientific exploration platform, but as an orbital weapons platform capable of deploying atomic warheads globally within hours of an order. General Curtis LeMay, then the Air Force Chief of Staff, described the concept privately as a strategic asset that could reach any target on Earth from a fixed orbit within 30 minutes. Dyson objected strongly to the military application. He continued to work on the project because he believed the peaceful applications, if the vehicle were ever actually built, would eventually overshadow the military ones. He later admitted publicly, wrong about that. Between 1959 and 1963, the Orion team completed detailed designs for the 4,000-ton spacecraft, the specialized launch facility at Jackass Flats in Nevada, the atomic bomb production infrastructure, and the crew selection and training program. Ted Taylor personally recruited the initial candidates for the flight crew. The total cost estimate for a functioning Saturn mission vehicle came to approximately $5 billion in 1963 currency. That was roughly 10% of the concurrent budget for the Apollo lunar program. For a fraction of the money going to the moon, humanity would go to Saturn. None of it happened. One meeting killed Project Orion permanently. On August 5, 1963 in Moscow, representatives of the United States, the Soviet Union, and the United Kingdom signed the Limited Nuclear Test Ban Treaty. The negotiations had lasted 8 years. The final signing ceremony occurred in the Kremlin, attended by senior diplomats from each of the three nations. Khrushchev signed for the Soviet Union. Averell Harriman signed for the United States. The treaty banned all nuclear detonations in the atmosphere, in outer space, and underwater. Only underground tests remained permitted. President Kennedy signed the American ratification on October 7, 1963, at a White House ceremony broadcast on national television. He described the treaty as a step back from the abyss of general nuclear war. The treaty entered into force on October 10th, 3 weeks before Kennedy himself was assassinated in Dallas. The treaty had been designed to slow the arms race and reduce atmospheric radiation from ongoing weapons testing. The negotiators in Moscow did not have Project Orion specifically in mind, but the treaty's language applied to any nuclear detonation in the atmosphere or in outer space, regardless of purpose. A spacecraft using atomic bombs to reach orbit would violate the treaty every second of its launch sequence. The Orion team at General Atomics understood immediately what had happened. Internal Air Force debate continued for another 18 months over whether to pursue an amendment to the treaty, specifically exempting peaceful pulsed propulsion. No amendment was ever formally proposed. The political appetite for exempting nuclear detonations from a nuclear test ban treaty did not exist in either Washington or Moscow. The Air Force officially canceled all Orion funding in early 1965. The final program memorandum was 5 pages long. It cited the treaty by name. Ted Taylor was 39 years old. He had spent 7 years on the project. He had left Los Alamos to build a nuclear spaceship. He returned briefly to weapons consulting work in 1965 and 1966, then left the nuclear industry entirely and spent the rest of his career campaigning against nuclear weapons proliferation and warning about the danger of terrorist theft of fissile material from civilian reactors. In 1974, the New Yorker writer John McPhee published a book-length profile of Taylor titled The Curve of Binding Energy, describing him as the man who had spent a decade designing atomic bombs and then spent the rest of his life trying to prevent anyone else from ever building one. Taylor's colleagues at Los Alamos considered his career pivot one of the strangest in American physics. The man who had designed atomic weapons for a living had become one of the most articulate voices in America, arguing that atomic weapons should not exist in any nation's arsenal. He died in October 2004 at the age of 79. Dyson wrote a paper in 1968 titled Interstellar Transport, describing how a scaled-up Orion vehicle using fusion pulses rather than fission bombs could reach the nearby stars within a human lifetime. The paper appeared in Physics Today and became one of the founding texts of what would later be called serious interstellar propulsion studies. Dyson himself never worked on Orion again after 1965. He returned to theoretical physics at Princeton and lived for another 55 years, remaining publicly convinced through the end of his life that abandoning Orion in 1963 had had been a historic mistake by the entire human species. The prototype hardware from Point Loma was crated and stored at General Atomics. Some pieces survived into the 1970s and were eventually donated to the Smithsonian National Air and Space Museum, where the Put-Put vehicle can still be viewed today. Other pieces were quietly destroyed during subsequent facility renovations. The complete technical archive was classified in 1965. Portions were released beginning in the 1970s under Freedom of Information Act requests. Most of the design documents for the actual atomic pulse units used in the propulsion sequence remained classified until 2002. Some remain classified today. The spacecraft was never built. The blueprints still exist, some at General Atomics, some at the National Archives, some at the Institute for Advanced Study, some at the Smithsonian, some possibly nowhere. The passenger version of Orion, the one Dyson called his favorite, would have carried 250 people, a complete self-sustaining biosphere, workshops, laboratories, farming decks, and equipment for a permanent settlement on Titan. Departure was scheduled for the American bicentennial in 1976 from a specially constructed launch pit at Jackass Flats. Ted Taylor was scheduled to be on board as chief systems engineer. Freeman Dyson had turned down an invitation to serve on the flight crew, citing his family, but had accepted a role on the mission planning committee. None of it happened. The Apollo program went to the moon instead. 6 crewed missions landed between July 1969 and December 1972. 12 astronauts walked on the lunar surface. The last human being to travel beyond low Earth orbit did so aboard Apollo 17, splashing down in the Pacific on December 19, 1972. No human being has traveled beyond low Earth orbit in more than 50 years. The space shuttle, which followed Apollo, could not exceed low Earth orbit by design. The International Space Station, which followed the shuttle, sits 400 kilometers above the Earth. Every crewed spaceflight since December 1972 has occurred within 1/100th of the distance to the moon. Human beings have not returned to the lunar surface. Human beings have not visited any of the outer planets. In 2011, the Defense Advanced Research Projects Agency initiated a small classified study on advanced pulsed propulsion concepts intended for crewed missions beyond Mars. The declassified portions of the study reference Project Orion by name. The classified portions have not been released. In 2019, a research group associated with Icarus Interstellar published detailed calculations for a modernized Orion vehicle using clean fusion pulses rather than fission bombs. The calculation suggested Saturn could still be reached in approximately 7 years with a crew of 250. The engineering has become somewhat easier since 1963. The political environment has become considerably harder. Freeman Dyson died on February 28, 2020, at the age of 96. In his final published interview, conducted 3 months before his death, an interviewer asked him what he considered the greatest engineering opportunity humanity had ever refused. He answered without hesitation, Orion. He said humanity had walked away from the outer planets in 1963 and had not gone back for them since. The blueprints still exist. Some at General Atomics in San Diego, some at the National Archives in Washington, some at the Institute for Advanced Study in Princeton, some at the Smithsonian National Air and Space Museum, some possibly nowhere. A spacecraft existed on paper that could have carried 250 people to Saturn by 1970. Its designers were an American weapons physicist and a British-American theoretical physicist working in a warehouse near San Diego. The first prototype flew successfully in November 1959. The full-scale version was canceled by a treaty signed in Moscow 4 years later. The blueprints remain partially classified. Nobody has built one since. Nobody has been to the outer planets. Nobody has left low Earth orbit since December 1972. The spaceship was never built. Almost nobody remembers why.